Hello, this is Chandrakala, Department of Chemistry, Hindustan Institute of Technology and Science. Today we will see about the determination of viscosity of a polymer using Oswald viscometer. Determination of viscosity of a polymer using Oswald viscometer. So first of all, what is viscosity? Okay, so what is viscosity? See, if you take water, all right, and oil, if you pour water on any surface, you could see it flowing freely, whereas when you pour oil onto the same surface, you could see it restricts its flow compared to that of the water. Okay, so the measure of restriction to flow of a liquid is said to be viscosity. Okay, so this will be the perfect definition for viscosity. The measure of restriction to flow of a liquid is said to be viscosity. So that is what we are going to determine today for a polymer. So the polymer that we are going to take is polyvinyl alcohol. Okay, so what is this polymer? So polymer means it's a combination of many monomers. Okay, when many monomers are combined under certain conditions of pressure and temperature, you get the polymer. For example, if you take ethylene, that is CH2 double bond CH2, if you polymerize it, you get polyethylene. Alright, so polyethylene you can simply write like this. If you take n number of the ethylene molecule, then you get a polymer whose structure can be written like this. So likewise, if you take vinyl chloride, alright, so you get polyvinyl chloride. If you take vinyl alcohol, then you get polyvinyl alcohol. So this will be the structure for the polyvinyl alcohol. We are going to determine the viscosity of the given polymer, that is polyvinyl alcohol, using Oswald viscometer. Okay, so Oswald viscometer, it is an U-shaped apparatus used to determine the viscosity. It consists of two bulbs here, upper bulb, lower bulb. Okay, and there is a capillary tube. Here is a capillary tube. Capillary tube, and you could see two markings here. One is the upper marking and another is the lower marking. Okay, so normally what we do is required quantity or known quantity of the liquid whose viscosity is to be measured must be added or drained through the limb that is having the wider mouth. Okay, and then it has to be pipetted out through the other limb that is having a smaller mouth. Alright, and you should bring it more than the upper marking, say for example here, and then you have to adjust it to this level, just like that, how you do the pipette and all, how you handle pipette and all. Okay, you have to drain it to this level, then you have to note down the time taken, so it will be in seconds actually, when the liquid flows from this marking to, from the upper marking to lower marking. Flow time you have to find it out. Okay, so different concentration of the polymer solution has to be prepared, and for each concentration as well as for the solvent you need to find out the flow time. Experimental portion, it involves 3 steps. Okay, step 1 will be the preparation of 1% polyvinyl alcohol. Okay, so 1% solution of polyvinyl alcohol has to be prepared. So this we can make it by dissolving 1 gram of polyvinyl alcohol in 100 ml of distilled water. Okay, so normally it won't get dissolved. We need to heat it to dissolve 1 gram of polyvinyl alcohol substance in 100 ml distilled water. So this is done first step. And step 2, we need to prepare different concentration of polyvinyl alcohol solution using this 1% PVA. So we will prepare 0.2, 0.4, 0.5, 0.6 and 0.8 concentrations of PVA using this 1% polyvinyl alcohol. So to prepare 0.2 concentration, we can take 20 ml of 1% PVA and dissolve it in 100 ml standard flask. If you want to get in lower quantity, then we can use we can take 2 ml of the 1% PVA and make it up to 10 ml. Then also we will get the 0.2 concentration. Okay. So likewise, if we take 4 ml of PVA, 1% PVA and make it up to 10 ml, then we get 0.4 concentration. And likewise for 0.5, 0.6 and 0.8. So this will be the step 2. And step 3 will be you will have to find out the flow time for the solvent with which you prepare the polyvinyl alcohol. Solvent is nothing but distilled water, so that we take it as T0. Okay, so you have to find out the flow time for the solvent using Oswald viscometer, and also you need to find out the flow time for every concentration: 0.2, 0.4, 0.5, 0.6, 0.8. So this is the experimental part, and under calculation part you need to do a graph that I will discuss soon. This is the table which will give you the details to prepare various concentration of polyvinyl alcohol. Okay, concentration of PVA solution of 0.2. If you want to make 0.2 concentration of PVA solution, then we have to take either 20 and make it up to 100 ml, or say let us take 2 ml now. Okay, so 2 ml of 1% PVA is taken, and then 8 ml of distilled water is added. Okay, we can make it up to 10 ml, or you can also say like 2 ml of PVA, 1% PVA, to that 8 ml of distilled water is added to get 0.2 concentration. So likewise 4, so ml is in common, so let me write just only 4 and then 6 ml of distilled water to get 0.4. 5 ml of 1% PVA mixed with 5 ml of the distilled water to get 0.5. Then it is 6 ml of PVA mixed with 4 ml of distilled water, 8 ml of 1% PVA mixed with 2 ml of the distilled water to get 0.8. Okay, so this table gives you the details of how you prepare various concentration of the polyvinyl alcohol solutions. And now let me explain you the observation tabular column. Okay, so first you will be finding out the flow time of solvent. Solvent here is the distilled water. Okay, 3 trials actually you need to do. So flow time of a solvent is represented as T0. Okay, so since we are doing 3 trials, take the mean of it and put it in second. Okay, so next you should find out the flow time for 0.2 concentration. Okay, so you should strictly go from the lower concentration only. Randomly you shouldn't take like first for to find for the 0.6 and then for the 0.2 and all. Okay, so strictly you should go from the lower concentration only. So after finding out the flow time for the solvent, you need to find out the flow time for the 0.2 concentration, and in between you need not wash the apparatus, just drain down the solvent and then you need to take the 0.2 concentration. So for that also you have to do 3 trials, take mean of it. Okay, so this is represented as T. Alright, then you have to calculate relative viscosity, so that is represented as neta R. Relative viscosity you can get it by dividing T naught. Okay, by dividing T with the T naught. T by T naught will give you the relative viscosity. Okay, and then you need to find out the specific viscosity. Specific viscosity you can find by subtracting 1 from relative viscosity. So specific viscosity is represented as neta Sp. Okay, so this is equal to relative viscosity minus 1. Then you need to find out reduced viscosity, which is neta Sp divided by C. Specific viscosity divided by the concentration will give you the reduced viscosity. So likewise you have to find it for all other concentrations. So first find out the T naught, then find T for other concentration, go from the lower concentration. Okay, so then you have to calculate relative viscosity, specific viscosity, reduced viscosity. Then you need to plot graph for reduced viscosity versus concentration. This is the Oswald viscometer, U-shaped apparatus consisting of upper bulb and lower bulb. So there is a capillary tube here. Okay, so one limb has the wider mouth, another limb is having smaller mouth. Actually we have to drain the solutions through this limb that is having the wider mouth. Okay, and after that you have to pipette out through this. So I think you could see 2 markings here, upper marking and then the lower marking. Okay, you have to adjust the liquid to come to this marking, upper marking, and then after that you have to start your stopwatch so that you can find out the flow time for it to flow from this marking to this marking. Okay, to prepare 1% of PVA solution, 1 gram of PVA substance is weighed carefully and then dissolved in 100 ml of distilled water. PVA doesn't dissolve in distilled water at room temperature. So first water is kept in heating mantle and then PVA substance is added to the boiling water. Solution is stirred well until it becomes transparent. PVA solution should not be used when it is hot. Okay, so it has to be cooled to room temperature. Okay, so when it is cooled to the room temperature, it can be used to prepare the various concentrations like 0.2, 0.4, 0.5, 0.6 and then 0.8. So now the solution is transparent. Okay, so it has to be kept aside to cool down to the room temperature. Okay, when it is cooled down to room temperature, it is ready to prepare the other concentrations. Okay, so step 2 is the preparation of various concentrations. So now I am preparing 0.2 concentration. So for that 2 ml of 1% PVA solution is taken in a 10 ml measuring jar and made up to the 10 ml. So that means 2 ml of 1% PVA and 8 ml of distilled water is added to it. 2 ml of 1% PVA is taken and then to that 8 ml of distilled water is added. Now this is transferred into a beaker, small beaker, okay, and then stirred well. The PVA solution must be mixed well with the water. Now the concentration is 0.2. So this must be labeled to 0.2. So I am labeling it as 0.2. Okay. Then next, to prepare 0.4 concentration, 4 ml of the 1% PVA solution is added into the 10 ml measuring jar, and then 6 ml of distilled water is added to it. Transfer it into a beaker and stir it well. Okay, so the PVA solution should be thoroughly mixed with the water. Now the concentration is 0.4, so it has to be marked as 0.4 concentration. So in the same way, other concentrations, that is 0.5, 6. Okay, then the third step is to find the flow time for the distilled water and also for the polymer solutions. So for this, first we need to wash viscometer thoroughly using distilled water. Just ensure that there is no any bubbles stay inside the viscometer, especially in the capillary tube. Okay, then if you find any bubbles, we have to blow and then drain it out of the viscometer. When it is thoroughly cleaned with the distilled water, now just measure 10 ml of the distilled water. So distilled water is the solvent with which the polymer solutions are made. So we need to find out the flow time first for the distilled water. So take 10 ml of the distilled water and drain into the viscometer through the limb that has wider mouth. Okay, just along the sides, in order to avoid the bubble formation inside the viscometer, we have to drain it along the sides. Then we have to pipette out through the limb that has got the capillary tube, or that has got smaller mouth. Okay, so we have to pipette out until it reaches a level just above the upper marking. So there will be marking, upper marking and lower marking. It should reach just above the upper marking. Until then we have to pipette out. Then adjust it to come to the upper marking. Okay, so when it reached the upper marking, we have to start the stopwatch. When the solution reached the upper marking, we have to start the stopwatch, and then we have to wait until it reaches the lower marking. So until then we have to hold the viscometer straightly. We should not shake the viscometer. We should not disturb it. So when it reaches the lower marking, that time we have to stop the stopwatch. The same way we need to find the flow time for all other concentrations of polymer solution. Okay, and then we need to tabulate. I have tabulated the values here that I have got while doing the experiment. 23 seconds is a flow time for the solvent, and for 0.2 concentration 36 seconds took, and for 0.4 37, and for the 0.5 40, 0.6 43, and 0.8 46 seconds. So you could observe that with the increase in concentration, the flow time also increases. Okay, then the neta R calculated for every concentration, that is neta R is equal to T divided by T naught. Then neta SP is calculated. Neta R minus 1 gives you neta SP. Okay, so neta SP divided by concentration was also calculated, and these values are plotted versus concentration. Scale is taken as 1 centimeter is equal to 0.1 units for both x-axis and y-axis. See, in the y-axis neta SP by C is taken, and in the x-axis concentration is taken. Concentration in the x-axis. Alright, so you get up points like this. So when you join the points and extrapolate it, it cuts the y-axis at a point. So that point is taken as the neta I. That is intrinsic viscosity. All the points may not coincide. Okay, if it is not coinciding, then maximum points we should make it coincide, and then find out the neta I by cutting the y-axis. Our aim of the experiment is to find out the viscosity of a polymer. So it cuts the y-axis at 0.23. Okay, so that's the result actually. But if you are asked to find out a molecular weight, then you have to use the equation that relates neta I with the M. But aim of the experiment here is to find only the viscosity that was found. Let's see the principle and application part of determination of viscosity of a polymer using Oswald viscometer. You are finding out the neta I, right? That is intrinsic viscosity of a polymer. So this intrinsic viscosity is related to the molecular weight of a polymer by an equation K m power A, where m is the molecular weight of the polymer, and this equation is said to be Mark-Hungowing equation, and K and A are constants. For this polyvinyl alcohol, K value is equal to 45.3 into 10 to the power minus 5, and A value is 0.64. Okay, so by the equation Mark-Hungowing, that is neta I is equal to K m power A, we can find out the molecular weight of a polymer. Okay, because all other values are known. Neta I value is got from the graph, K and A values are constant, and M can be found. We can find out the M, molecular weight of polymer. And knowing the molecular weight of polymer, we can also find out the degree of polymerization. Degree of polymerization. Simply we can represent it as dP. So that is equal to M, that is molecular weight of polymer, divided by M naught, molecular weight of monomer. So monomer, here is that we have taken here is the we have taken polyvinyl alcohol, right? So that means the monomer is vinyl alcohol, that is CH2 double bond CHOH. Its molecular weight is 44. Okay, how will you find that? 12 is atomic weight of carbon, so 12 into 2, 24, hydrogen 4 hydrogen, so 4 oxygen, atomic weight is 16, so you will get 44. Okay, so 44 will be the molecular weight of our monomer. In molecular weight of polymer, you can get it from the Markov-Howing equation. Alright, okay. Hope you all understood the experiment. Still, if you have any doubt, you can ask me through your comments. Meet you all in next experiment. Thank you.